I'm on a mission from a higher power in the universe. And that mission is to convince you, and I would like to convince the EE people as well, that things are going well, you're addressing necessary questions, but I read in a lot of the journal articles and things that I've seen at this meeting and so forth, a very casual approach to system science. In fact, everybody talks about systems thinking. And that's great. The more of us that are thinking systemically, and who knows what that actually means, that's great. But it isn't enough. It's not enough to do real hard science. And so what I'm wanting to do is convince you that system science has a role to play in both biophysical and ecological economics, and let's see, there we go. System science has been sort of languishing since the 50s, when a number of different clearly related fields, like cybernetics and information theory and things like that, sort of started tracking off. And the reason they did it was very simple. You don't get tenure unless you get published in a specific journal and prove to your comrades that your tribe that you know what you're talking about. And so that pretty much took place. But more recently, there's been a resurgence of interest in coordinating, making a system out of system science. And so that's actually going on today. I've been very fortunate to be participating in the International Society for System Science, which is the oldest one. You would recognize the names. George Clear was one of the more recent, 10 years ago or so, presidents of that society. And so the people in that society have begun to realize that we need to bring it all back together again, and we need to do really hardcore system science. The International Federation for Systems Research is another very old organization, going back, actually I don't know how many years, but there are about 40 organizations that are members of that. And I'm going to hope to convince the board of ISBPR, that BPE, that we need to be in that group. The biggest development, of course, was a textbook, a comprehensive textbook on system science that addresses an undergraduate level understanding and covers everything, we think, everything that's currently known. So that's possibly going to help a great deal. So these are, and the interest, increasing interest in the systems topic in education is being driven now by NSF. I don't know how many of you are familiar with the next generation standards for STEM education. Anybody heard of that? Okay, almost everybody. So that is playing a very large part in driving things like Common Core and other aspects of K-12 and beyond education. And they have insisted now that we include in cross-cutting themes, which are a part of that standard, developing standard, systems, concepts. And so there's some official drive in that direction. Just very briefly, the principles book contains these 12 principles and a bunch of derived principles from them. I'm not going to go into them right now. I just wanted you to see that they exist. And we have, my co-author and I have been working on some organizational ideas to show what these principles sort of mean, what they contribute. Overall organizing principles, auto-organization, which most of you probably know is self-organization, but self is such a terrible term. Auto-organization, emergence and evolution, then these core principles, which are true, can be found in every single system, and for which there's really good mathematics that we've developed. And then the operational principles get a little bit mushy, but they do, notice one of them there is governance. Understanding, the fact that a system can be understood is really quite extraordinary. But in any case, that's just to let you know what the background is. So what I've been working on for the last 2 years, and these are the results that I'm going to be publishing, presenting in July at the International Society of System Science meeting in Boulder, Colorado, is an expanded formal definition of system. And I was going to, by the way, I came prepared for a half-day workshop, which is what my proposal was. Somewhere along the way, it got shifted to a 20-minute talk. So I'm not sure what happened, but I've got a whole bunch of slides here, and I'll just have to go through them. I'll just punch through them. You won't see much. If you really are interested in it, of course, it'll be available on the website. Anyway, the idea here is, and this was actually inspired by the work of George Clare, who was a mathematician primarily, and so he wanted to play with the math. I'm a little less of a mathematician, a lot less of a mathematician, and more interested in doing something that has a practical result. So maybe I should call this applied instead of theoretical. In any case, we define system as a set of components, network of relations, an environment that includes sources and sinks, and the other terms are not quite as important. Well, they are important, but they're a little more complicated to express. And all of that happening at some time differential. But the two important points here that I want to bring up. We've had a lot of problem in system science, and a lot of the work that some people in this room have done has been problematic with respect to choosing boundaries. And there's a lot of argument in the systems world about what a boundary even is, including some statements that there are no boundaries. It's what the modeler chooses. And that's exactly right. When you want to build a model, your motivation is different from wanting to analyze the system. Now, you may not believe that, but I've done lots of systems, and I kept asking myself, well, wait a minute, what's going on here? Why am I having difficulty with this boundary definition? And I'll show you an example of it. One of the exercises I was going to do was to actually walk through a boundary analysis so that you could see how you can apply this hard-nosed system science to actually doing it. Okay, so anyway, the bottom part there, the equation 3, is the real secret. When Gail was talking about hierarchies, that's where it comes from. That's a recursive definition that allows us to go down many levels, and a system is actually decomposed into subsystems and subsystems into subsubsystems and so on and so forth, down to some componential level. So I'm just going to whiz through these guys. And the thing that I'm working on, so once we have this definition done, the next step is to define an ontology, or a language, for system that will fit into that particular model. And so I've been working on that as well. And once you've got that, then you have the basis for developing a platform for simulation. So it'll look a lot like system dynamics. If any of you have played with system dynamics languages, it's going to look a little bit like that in terms of how it actually plays out in creating models on a computer and so forth. But there will be substantial differences. So that's the idea, is develop a more comprehensive language of systems. With that language of systems, there are going to be a lot of benefits. One is that people who've been talking past each other, having issues with what other people are saying, are going to be able to pin down and speak a common language about those issues. That's what I've been sort of witness it today, but it's all over the place. People have to have a single language that they can speak before they can actually start to communicate. Let's see. So the system ontology is fairly well developed, and not spend a whole lot of time on that. Here's an example of lexical elements, graphical. These are icons that would be used in the computer front end to do this. And I just wanted to point out that there are historical precedents. So none of this is necessarily new. It's just putting it together in a new way. Howard Odom, for example, had a lot of those things. His semantics were process-oriented semantics. He had producers, consumers, things of that nature, and energy flow and things like that. Jay Forster's approach was he was just interested in dynamics, wanted to see what the graphs look like, and so he just modeled everything in stocks and flows and influences. And so those are all necessary parts of it, but nowhere near sufficient to really cover the span or the expanse of general systems. This simply shows how some things get derived in the language. What I'm going to be doing is taking these primitives, these upper level primitives, and actually showing how they break out into specifics. And then at some point, for example, the word agent down there is a general process, a decision process. And there are different kinds of agents, so we can derive further. If any of you are familiar with object-oriented languages, like C++ or Java or something, this is the same basic concept that I'm going through. That evolvable tag, I'll maybe talk a little bit about it. I can't really go into this too much. This is a claim, and I argue it in the book, that all biophysical systems have these fundamental processes going on inside. So here's the system view using that system's language. Nowhere near enough arrows. Can't show all the flows. But just getting the idea of what all systems, whether we're talking about a single cell organism, a whole organism, an organization, a country, it doesn't matter. They're all going to have some aspects of these fundamental processes. So we can begin to build our models or have a meta model that we can start with and then fill in the pieces in the order. And this is what it's all about. I am motivated by the fact that the human society, the human social system is out of control. And I think almost everybody in this room is pretty much in agreement with that. And so this is basically looking at the Earth as a semi-closed system with respect to material and an open system with respect to energy flow. I'm working with the IFSR on developing a system science. How do we promulgate system science to the rest of the world based on the motivations of this thing? All right. So anyway, I look at the human. This one. No, I guess I shoot. How do you do that? Oh, there it is. So typically, when you look at something as complex as a human social system, you're just going to see this blur. There's people, there's technology, there's all kinds of stuff going on, and at first glance, it really looks problematic to study. What in fact is happening is that you're looking at a fuzzy, a bunch of fuzzy sets. The systems themselves are fuzzy sets. Each one of those represents, and this is not meant to be complete, it's just a representation of different component activities within the human social system. With humans in the center, humans in the center here, and here's, that's the big orange arrow. And then here's the economy, which is sort of the next biggest thing, and some of the other aspects. And it just, this looks unmanageable. Imagine the data you have to look for in order to tease this thing apart. But it turns out that boundary analysis in system science actually will allow you to start to pull those things apart and treat them as whole systems in and of themselves, subsystems of the larger system. Yes, 3 minutes, okay. Going right through the whole economics stuff. You get right to the end here, which basically is, this is going to be one of the exercises, is determining the sustainability of solar, in this case PV, say, a solar economy in which you have not only the T there, the free energy to the society, on the one hand, coming from some set of solar collectors. But then you have to work back and say, how did those solar collectors get there in the first place? They had to be manufactured, they had to be deployed, they're going to need repairs, and so on and so forth, which means you either take energy away from T, or you have a set of solar collectors that are dedicated to providing that. And the big question for all those energy flows that you see there, the big question is, can the total energy that's being used in order to produce the solar collectors for society exceed the that energy? So in other words, this is asking the question: can we produce a solar society using solar energy and not oil, gas, and coal, as is currently the case? I don't know the answer to that, but I know how to build a model. So if anybody's interested in the boundary analysis approach to getting there, and that's it. That's the whole workshop in 20 minutes. If you are interested in the systems part of this stuff, I've got some web links there that you can go to see what the ISS has for.